as an on switch or an on state. On reverse biased, abbreviation RB for reverse biased, FB for forward biased. For reverse biased, I'm changing the polarity of the supplied voltage. Negative is to the cathode, positive to the negative to the anode, positive to the cathode. If the voltage is less than 0, you notice that the Vs is less than 0, means that it's a negative voltage. The diode is in reverse bias and there is no current flowing through the diode. If there is no current flowing through the diode, I can model, or I can say that the diode is in off state, or the diode, it will act as a switch in off position. Now that's the discussion that I will make in a bit later. Now putting the forward biased and the reverse biased and the IV characteristic, or the IV or the VI characteristic. I said that the current is a function of the applied voltage across the diode, and most of the time I will refer as the IV, but in the same time some other textbooks are referring as the VI characteristic. That's, on the right side of the graph is the forward bias. On the left side of the graph is the reverse bias. You notice that, again, in the reverse bias, that current is very small. And I mentioned a few times that current is in terms of nano or micro amps. Most of the time we are ignoring, we are making the assumption that if the diode is in reverse bias, the current is equal to 0. If the voltage applied to the diode it's above 0.7 volts, the current is, or ideal, it's an infinite current, but it's limited, and we have always, the resistance connected in series with the diode that it will limit the current flowing through it. And that's the example that we discussed, and that's why I'm trying, to have, everything that I'm writing like, the whiteboard or the blackboard in class. And the example, this example, part A is already on D2L on my notes, but I extend that finding the current to the diode if a resistor or a group of resistors is connected across a diode. And that was, the example that we discussed. We are applying the KVL in a series type circuit. The Vs is the sum of the two voltages, the VR, voltage across the resistance, VD, voltage across the diode. From this equation, I can find the VR, knowing that the diode is in forward bias, and the VR in this example is 11.3, that's 12 minus 0.7, which is the VD in forward bias, which makes, the ID current. Now, always, look for an equivalent circuit like this. Instead of having, the resistance R, I may have, a group of resistors. Instead of having, just a diode, I may have, multiple diodes connected in series. And instead of resistance R or R1, I may have a group of resistors that may be connected across a single diode or two diodes or three diodes. Now, to simplify, any of the, let's say, complex circuit that has, multiple resistors, multiple diodes, always look for a configuration that looks like that. A resistance or an equivalent resistance series with one or multiple diodes connected in series. You notice that I'll try to keep it simple, and always I'm making, the resistance or a group of resistors connected in series with a diode, or, multiple diodes, or a group of diodes connected in series. Always, simplify the circuit that looks like, this one. The resistance and a diode or multiple diodes connected in parallel with the resistance or a group of resistances. The example that I made is suppose that I'm adding, the resistance R1 parallel with the diode D. Now, I'm still applying, the KVL in this loop. We did that, and we determined the VR. In top of that, we can find the total current or the current I. Now, you notice that this current is divided in two branches, into branch currents, the ID and the R1, or simply I1. Now, the current I, or the total current, is the ID plus the I1. Means that first step is in order to find what is the ID, is determining what is the current that flows to through the resistance R1. What we know at this point, the voltage across the resistance is actually the voltage VD across the diode. Means that to determine what is the current flowing through the R1 is the VD over R1. That's 0.7, 700 ohms, gives you, 1 milliamp. From the previous step, or from previous part A of this example, ID is the I minus I1. That's 3.4 minus 1 milliamp, means that the current that flows through a diode D1, ID is 2.4 ohms. Over the weekend, I will try to make another example, or another 2 examples, which will be posted on D12, probably by the end of Saturday or Sunday, which helps you, to practice and see, the approach of how to solve a series parallel circuit with diodes. I'm talking about, the DC type circuits with multiple diodes and multiple resistors connected series or parallel. Now, today we'll start going into a rectifier. Now, before I'm going to the notes that I already, posted on D12, and it's, similar with the diagrams that are on D12 on your textbook, I will make, a short review, and I mentioned from the beginning of this course to review the AC quantities. Now, I'm going back, to the handout, and I try to draw, using the mouse. That's why it doesn't look, very nice and neat. But anyway, I'm trying, to recall the AC and the DC representation. Now, from this diagram, you notice that a DC, we can represent a DC current or a DC voltage as a straight line. Looks like, again, it is a straight line. And I'm assuming that, that's a DC representation of, a current or a voltage. Now, for AC, and I'm asking, one more time, to review the AC theory. I'm using peak, peak-to-peak, average, and the RMS. Now, the question is how we can approach, how we can actually analyze or see what happens if an AC voltage, that's the AC voltage, is applied to a circuit. What that means? It means that, I may use, this circuit or the other circuit. Means that the diode may be in forward bias or reverse bias. That's why I start using, the DC voltage source for a diode, or using a DC voltage source for a diode in forward bias and reverse bias. Actually, how we can analyze, and from now on, that's, the idea of analyzing a circuit, an electronic circuit, with an AC voltage source. Now, to remind you about, the AC voltage source, how we can draw, the AC voltage source for the first half, I'm making the assumption that, it's positive. For the second half of the period, the voltage is negative. What that means, again, as a positive, I can reverse, this 2 halfways. I can start with negative, and after that, with the positive. Remember that the AC voltage source has those two, is changing the polarity after a given time. In this, full sine wave waveform, I'm having, half of the period as the positive, half of the period as the negative. Now, aside, I'm writing what that means. It means that I have to make an assumption that one of the two terminals is positive and the other terminal is negative. Okay. If one of the two terminals is positive, the other one is negative, I will assume that that's, the positive halfway, and that's, the negative halfway. Now, how we can analyze, how we can look, for the circuit that has an AC voltage source? We are taking, the first assumption for the first halfway. Means that I will assume that, for the first halfway, means that I'm still, in the first half of the period, that the positive or the polarity of the AC voltage source has the positive on top and the negative on the bottom. Means that I will analyze the behavior of the circuit when the positive region or the positive area of the sine wave is applied to the circuit. Now, I'm asking, one more time, and for clarification, what means rectification? I mentioned a few times, the rectification, and I'm using from now on, for the next 2-3 lectures or in this unit or the second unit. What means rectification, please? And what's the purpose of a rectifier? Conversion from AC to a DC. Again, this is, what you are looking for. That's great, Graham. A rectifier will convert an AC voltage into a DC voltage. Okay, now I'm going back to these two diagrams. That's why I'm put them, side by side, because I'm using them. Now, in forward bias, remember that the current flows through the diode. In reverse bias, there is no current that flows through the circuit. A rectifier allows the current to flow in a single direction. Actually, the first step or the halfway rectifier, we are looking to do what? To get rid of that negative side of the sine wave. If I can get rid of the negative side of a sine wave, I can make the current that flows through a single direction. Sorry, that's using means that if I can remove that negative side of the sine wave, the current flows in a single direction. Here you go. That's, the first application, the simple application for a diode. How we can achieve that? By simply, placing an AC voltage source into a circuit. Now I'm substituting actually the DC voltage source with an AC voltage source. And I'll have, the same approach. Suppose that I'm removing this DC voltage source with an AC voltage source. And the first assumption is that, I'm applying the positive of an AC voltage source on the top, the negative is on the bottom. Actually, if I'm looking, in the notes and on your textbook, this is what we have made, is the DC voltage source, which is replaced with an AC voltage source, making the assumption that, for the first half, the positive, the polarity of the AC voltage source, the positive is on top and the negative is on the bottom. You notice that for the first half, notice that the positive of the voltage source is connected to the anode. The negative of the diode is connected to the resistor and back to the negative of the voltage source. And the diode, it will act as a switch closed, or the switch in on position, or the diode is in on state. That's why I put, those two diagrams, side by side, or, one underneath, each other, showing that the voltage is positive. That's the VP. That's the input voltage. That's the V in for the first, for the first half. The voltage is positive. The diode is forward biased, and the diode is in on state. The current it's flowing through the circuit, means that there is a voltage, or there is a current that flows through the RL, and there is an output voltage. That's the V out. That's the voltage across the resistance based on the diode being in on state. Now, we are looking for the second half. Now, let's go back in the two circuits. Again, I'm applying the positive to the anode and the negative to the cathode. I said that for any voltages above zero, or any positive voltages applied to the circuit, would be like switching. Exactly. That's, another approach. And that's why, I will leave, this remark, or this note, to the end of, the presentation, because it's actually like switching between on and off, reverse and forward bias for a diode. But you're right. Okay, now going back, to the forward bias. For the first half, the diode is in forward bias. The voltage is greater than zero, means that it's a positive voltage applied across the diode, and the current is greater than zero. Now, going back to the diagram, you notice that for the second half, the voltage AC, or the AC voltage, or the V in, change the polarity. Means that in the handout, I am here on the negative side. This is what we are looking for. Actually, we are looking to suppress. We are looking to remove that negative side, or the negative half of the sine wave. On the second half, the polarity of the AC voltage source is the negative on top, means that the negative is applied to the cathode, to the anode, and the positive through the RL is applied to the cathode. Looks like, the diode is in reverse bias. In the handouts, the diode is in reverse bias. Looks like, the VS, the negative, is applied to the anode. The positive is applied to the cathode. What that means, the ID is equal to zero. And that's, very important to see that the current is equal to zero. What that means, the diode is in off state, or there is no current that flows through the circuit. Going back to this diagram, you notice that for the second half, you notice that I'm in this negative side of the applied voltage. When the diode is in reverse bias, there is no current that flows through it. You notice that the current is equal to zero. Means that we can replace the diode with an open switch. If we are replacing the diode with an open switch, the circuit becomes an open circuit. Now, I'm recalling again, the open circuit. What are the two characteristics of an open circuit? Remember that in terms of the current, in terms of the resistance. We covered that in 105, we review that in 205. What are the two characteristics of an open circuit? There is no current and infinite resistance. That's perfect. And the current, you notice that is zero, means that the diode, it will act as an open switch or an off state, or the diode is in off state. Means that if there is no current, the voltage across the resistance. What is the voltage across the resistance if there is no current? Ohm's law, isn't it? Is 0 multiplied by the value of Rm, means that the V out or the output voltage is 0. Make sure that you understand, the concept of the open circuit. And I mentioned that I'm using intensively in 105, 205, and especially in 350 at this point. You notice that the diode is switching between on state and the off state. What that means, going in the handout, the diode, the circuit is acting as an, having, the diode, and the diode is acting as a closed switch or on state, and the off switch, which is the off state. At this point, again, we can have, a switch with two voltage sources side by side. One is positive, one is negative. And suppose that, that switch is moving or is switching between the two voltage sources. Means that the diode will be in on state if it is forward biased, and the diode, it will be on off state if it is in reverse bias. In the same way, we can look at the behavior of the circuit if the AC voltage source is applied to it. There isn't enough voltage for the current to exist in reverse biased. And I mentioned that, Graham, this reverse current, it's very small, milli or nano amps. That's why in calculations, we are not taking, the reverse current into account. That's why we'll approximate the reverse current as being equal to 0. It's too small to take it into account. The other current, ID, most of the time we are dealing with milliamps, amps, 10 amps, 100 amps, means that is way much higher compared with the reverse current, which is in terms of the milli or micro amps or nano amps. Milli, probably, just few milliamps, but I'm comparing milliamps with hundreds of milliamps or tens of amps or hundreds of amps. That's why the reverse current is not used in our calculations, in our problems. Again, it's just, the basic, and that's why we are not taking into account the reverse current. Did I answer your question? Okay. Now, going back to this diagram. Okay, now for the positive half or the first half of the sine wave, I'm making again the assumption that, the first half it's positive polarity, or the positive terminal is applied to the diode. The diode becomes or is in the forward bias or the on state. The current is flowing to the circuit, and this is what you want to achieve. The current that has a unidirectional, or it has, a single direction. For the second half, the negative half of the voltage source or the waveform, the diode is in off state and there is no current that flows through it. Means that the first achievement or the first part of having a rectified voltage is achieved. Again, it's the simplest rectifier, and it's called, the halfway rectifier. Now we may notice that, half of the the sine wave of the input voltage is rectified, and just a portion of the just half of the waveform is over a full period of the sine wave. Going, in the notes, I mentioned that, the V in positive, the diode is in on state when the input voltage has a reverse polarity. The diode is in off state. There is no current that flows through the circuit. Means that we made, the first step. We convert an AC voltage into a DC voltage. The current, again, the current flows into a single direction, means that the current flows through the circuit. When the positive is applied to the anode, the negative is applied to the circuit. Now we talk about, the PIV. This is probably the most used notation for the peak inverse voltage. In the same time, you may see the PRV or the VBR, and I mentioned that. Always, the peak inverse voltage, when the voltage or the input voltage is in reverse or has, the opposite polarity, means that the voltage applied to the anode is negative and the voltage applied to the cathode is positive. That's very important to understand that, always, the breakdown voltage or the PIV has to be greater than the VP. And I mentioned that one of the 4 or 5 important characteristics, it's the peak inverse voltage or the PRV. And this is what we are looking for, to make sure that, the diode can sustain or can resist, to the inverse voltage that is applied across the diode in reverse bias. Usually I mentioned that, or as an example, suppose that the voltage applied to the diode is 200 volts. I'll choose a diode that has the PIV or the reverse voltage as 250 or 240, in this range. Always, has to be greater than the applied voltage. That's from practical point of view. We may see the VP and the VM, which has, the same meaning. Remember that that's the maximum voltage, which is the same thing with VP. That's why I may choose, to switch, between the VP and the VM. Just to remind you, the maximum voltage is the same thing with the VP. That's the peak AC voltage, PIV. That's, the most used one in my notes and my course. In textbook, the peak inverse voltage. Now, the question is, when the peak inverse voltage occurs, when the diode is in reverse biased. If the diode is in reverse biased, we mentioned that it will act as a switch in off position, means that this circuit this circuit becomes an open circuit. There is no current that flows through it. The question is, again, what is the voltage across the resistance if there is no current? The voltage is 0, isn't it? Now, if the voltage is 0, I'm looking to determine what is the area or what is the average voltage across a full period. Remember that a full period is 2 pi. But for the second half, the negative side of the sine wave was removed, from the graph. Means that I have to calculate the area underneath only the positive half of the waveform. And I'm spreading this area over the 2 pi, over the full period of the sine wave. remember that in ELE 205 or 105, we discussed about the average, which is the same with the VDC. This is, the DC component or the average value of a DC voltage source of the rectified voltage of or a halfway or a full wave rectifier. If we know the VP and the area, the positive area, but spread it or over a full period, you notice that again, the second negative or the second half of the sine wave is suppressed, is removed from this graph. Means that initially we discussed about the average as 6.3738, 6.37 VP. But this equation or the initial equation is for a full sine wave. Half of this quantity of this factor 6.38, which is or is the meaning of just a single half of the sine wave spread it across or along the full period is actually the VP over the 2 pi, the average, which is actually 0.318. You notice that the only difference is that factor, which is 0.318 instead of 0.637. Actually, it's half again of the VP because a single half of the sine wave is spreaded for a full period. When we have, a full sine wave, both areas are spreaded or are making, the 0.637 the VP. That's why you have, just half of that initial factor, 0.637 as 0.318 for a halfway rectifier. The VP or the VRM, the VM as the maximum or the peak voltage. Now, in terms of the output power. Now, in order to determine the output power, looking, in, this circuit, I'm having, the supplied voltage, and the supplied voltage most of the time is more than 0.7 volts. We are taking into account the voltage drop across the diode. Don't forget about, the barrier potential. The voltage, it will act as an on switch for any voltages, especially, the above, 0.7 volts means that the voltage drop across the diode is 0.7. To calculate the output voltage or the V out or the voltage across the resistance RL, which is actually, the output voltage, is the VP in, which is the peak input power minus the drop voltage across the diode. That's your VD, the voltage across the diode, which is, forward biased. The voltage across the diode in forward bias is 0.7 volts, and the KVL applied in the simplest circuit, which has the voltage source, the diode, and the resistance RL. Means that to determine the peak output voltage is the peak input voltage minus the 0.7. You notice that the peak quantities, peak output quantities, or the average output voltage or current, or the average output power, always uses the average input voltage, the average input current, and so on. Depends on what is asking for. I can ask, for the average power. If I'm asking for the average power, I'm using the average voltage or the average current or both of them. If I'm asking for the peak output power, what we are using? The peak output voltage, Knowing the resistance, we can determine the peak output power. In the same way, I may ask, the RMS or the DC output power means that I have to use the RMS voltage or the VDC. Using the RMS or using the average gives you the average power. The RMS gives you the RMS power. Using the peak gives you, the peak power. That's why in the problems that will be given in the assignment and test, pay attention for what is asking. I may ask, for the peak current. What do you know? If we know the peak voltage, we can find what is the peak current. The peak current through the diode is the same thing, or is the same, or is equal to the peak current through the load, being a series type circuit. Remember, the series and the rules for series and parallel type circuit. Again, the diode is in reverse bias, and that's actually the peak inverse bias, peak inverse voltage, or the PIV. The diode is in reverse bias. The diode, it will act as an open switch. The entire voltage or the peak voltage applied from the voltage source, now it's applied across the diode. That's why, the diode has, the highest, let's say, electrical stress in the PIV, not the reverse bias. Not the forward bias. The forward bias, we know that the voltage is 0.7. The highest or the largest stress in forward bias is in terms of the current. Means that we have to make sure that the load resistance is not lower than the maximum. It will limit actually, the maximum current that can flow through the circuit. That means that I cannot go, lower than a certain value. Based on the maximum current that can flow through the diode, I can determine the minimum current that is connected across the circuit. Now, another consideration is if I'm looking, in the initial circuit. Now the question is, suppose that I'm reversing the diode. What that means? I'm taking, the diode and I'll reverse. I'm switching, the two terminals of a diode. If the diode is switched, is reversed, or has, the reverse connection in the circuit, or the opposite connection as the initial circuit, you notice that if the positive is on the top, the positive of the voltage source is applied to the cathode and the negative was applied to the anode. Means that for the first positive half of the waveform, the voltage is 0 because the diode, it will act as an open switch and there is no output voltage or there is no current. For the second half, the negative is applied on the top and the positive on the bottom. Means that the diode now is in forward bias. There is a current that flows through the circuit, but you notice that the current flows in opposite direction. Means that the diode still, it works like an on-off switch, except that the current flows in opposite direction. I may ask, what will be the change in this diagram? If the diode is reversed, is based on, again, the last diagram. I may use, a different color, let's say, the green. Now, if the diode is reversed, I may obtain, still a DC voltage. Remember that a DC voltage or a DC current current flows in a single direction or is unidirectional, except that instead of removing the negative side, if the diode is reversed, I'm suppressing, the positive side, and only the negative side, it will be across the RL, or the output voltage. Means that reversing the diode, it will change the direction of the current, means that I will end up with a negative voltage or a negative rectified voltage across the resistance RL. Again, I am assuming that nothing else is changed in terms of the ground or in terms of the connection between the voltage source and the resistance. The amplitude of the output voltage stays the same. Nothing is changed. In forward bias, remember that I'm having the supplied voltage, KVL applied in this loop, the supplied voltage minus the drop voltage across the diode makes the output voltage. Now, make sure that you get, the idea about, reversing the diode and the diode in the initial position or the initial connection. That's, positive connected to the anode connected to the voltage source, or the cathode connected to the voltage source. Most of the time you will see, one of the two circuits. I may give you, a circuit that has, the diode in this way connected, or the diode connected in the other way connected, or the reverse way connected. Any questions, comments, concerns? Monday, again, to remind you, Monday I will give you the paper version of, or I will hand out, the assignment one. I will make, copies today just to make sure that everything will be ready for Monday. A week later, and all these dates are already on detail, and I'll remind you, Monday. Monday you have labs. It's still in the hands-on lab. Make sure that you have the safety glasses and the safety boots, and face mask is mandatory. Any questions, comments, concerns, please? Yeah, usually long pants. It's a good idea. Any other questions, please? If you don't have any questions, have a nice weekend, guys. Thank you.